Hello all, welcome to the course on digital signal processing. Myself Shoham Chakraborty. Let's move on to our lecture 2, basics of sampling and reconstruction. All right. So let us have a quick review of what we are going to cover in this lecture, or what are the topics that we are going to cover in this lecture. So first topic that we will see, that sampling of signals. So we will understand that how signals are actually sampled. Okay, so the basics of sampling will be covered. And the next is the reconstruction of signals. Most importantly, how are signals reconstructed? Reconstruct means when a signal is sampled, it is basically changed from a continuous time signal to a discrete time signal, and reconstruction is recovering that discrete time signal back into the continuous time form. That is called reconstruction of signals. Then we will understand the sampling theorem. Okay, it's very important theorem in terms of signal processing, one of the basis of sampling, and obviously why it is important, the importance of the sampling theorem. So now, what is sampling? Let us see what is sampling. Now, sampling is nothing but it's a technique to convert a continuous time signal to a discrete time signal. So sampling is basically nothing but it's a technique by which we can convert a continuous time signal to a discrete time signal, as just I've said. And how is sampling done? That is the next question that comes to our mind. Now, sampling is basically performed by using impulse signals. So we have learnt about impulse signals in the previous lecture, maybe about lecture 1 or so, or maybe we'll see more about them. So impulse signal is it's a basic signal which is used in signal processing. Okay, so we'll learn more about that in some other lectures or so. And there are circuits basically which can perform sampling. Now, one of the most good example of a circuit which performs sampling is a sample and hold circuit. A sample and hold circuit is a circuit which uses a capacitor to charge and hold that charge for some particular instant of time. So that is called a sample and hold circuit. So that is sampling. So by sampling, we mean that we are trying to find out the value of a signal at a particular time instant. That is called sampling. Okay. And yes, the third point is very important in this case, that is the sampling rate. Now, what is the sampling rate actually? Sampling rate is basically the frequency. It's the number of samples which are performed or which are obtained in a second. That is called the sampling rate. Sampling rate has got a major role to play in this process of sampling. And sampling frequency, usually the time interval after which sampling is performed, that is called the sampling rate, and the frequency at which, that is 1 by time period, so 1 divided by the sampling rate is called the sampling frequency. Okay, and obviously we must understand that greater the number of samples, greater will be the chances or probability to recover those samples. Okay. Now, sampling a signal, as you can see over here, you can follow my mouse. You can see at 0, 1, then 2, 3, 4, at every, see about t interval of time, 1 is the first sample, 2 is the second sample, 3 is the third sample, so 4, 5, 6, 7, 8, 9. So we are trying to find the values at a particular point of time. What is the value of the signal at a particular point of time? That is called sampling basically, okay? And that is given by like SI, ST or so. So this is what we mean by sampling a signal. Here you can see a continuous time signal which is sampled so easily, right? Reconstruction of a signal. Now how do I do that? How do I reconstruct a signal? Okay, let's see. So yes, this is the reverse of sampling. That means if sampling is conversion of a continuous time signal to discrete time signal, the reverse of sampling is called reconstruction. Okay. Now what happens in reconstruction? A discrete time signal is actually converted to a continuous time signal. So if I have a discrete time signal, so that signal is basically converted to a continuous time signal. Okay. Now this is reconstruction. Now reconstruction may be possible, may not be possible. Okay, so the accuracy of reconstruction is important. That means the continuous time signal that was converted to the discrete time signal, so it is very essential to recover almost the exact replica of the continuous time signal that became a discrete time signal. So it's very important to get an exact replica of that signal. Okay. And yes, the fourth point, reconstruction may be or may not be possible. Now, if the number of samples of the signal are not quite large enough, say in an interval, say for example, if I have a periodic signal with a time period of about say 10 seconds. Now in 10 seconds I have only 2 samples. So if I take only 2 samples within 10 seconds, then I may lose important information which I might get from that signal. Okay. So as a result of that, it's very difficult to get back the actual signal. Okay, so that's why that is the job that is played by reconstruction. So reconstruction may be possible, may not be possible. Okay, it's not always true that we can always reconstruct a signal. Okay, it's not always true. And this probability of reconstruction, that means whether it is possible to reconstruct a signal or not, that is dependent on the sampling rate of a signal. And here you can see that these are the two you can say theorems or algorithms probably by which we can reconstruct. One is called a zero order hold, the other is called a first order hold. There are other ways also. Now zero order hold applies it uses a rectangular pulse. Okay, so what does it do is that it takes the samples and simply joins them like this. So you get an approximate signal like this. Okay, and first order hold is done by using a triangular signal. Okay, so that is called a first order hold, by which we can approximate a signal. You can see that as we increase the hold, that means first order, second order, then the better approximation or the better chances are that we can actually get back the original signal. Okay, so this is basically an approximation technique that we apply over here. In fact, now also whenever I am speaking, so my voice is a continuous time signal that is getting sampled and getting converted to a discrete time signal, and then it's getting quantized, becoming a digital signal, and then it is stored in my machine, right? Now when I'm trying to listen to that video, what is happening is that I am actually reconstructing back my discrete time signal that is actually stored, or the digital signal that is stored on the computer. Okay, because I won't be able to listen to a discrete time or a digital signal. So humans can only recognize analog or continuous time signals, mostly analog signals. Okay, so it has to be reproduced. That is a signal reconstruction, basic example. Okay, and finally the sampling theorem. So what is the sampling theorem? Now sampling theorem is also known as Nyquist's criteria for sampling, and Nyquist's criteria for sampling is mainly applicable for a band limited signal. Well, band limited signal is a signal whose frequencies range from a minimum frequency, maybe it's mostly it is 0 up to a maximum level of frequency. It's called a band limited signal. Okay. Yes, and this is the sampling theorem. Fs greater than equal to 2 fm. So what are these actually? Fs is the sampling rate and fm is the maximum frequency component that is present in the signal. So if I have a signal which has got several frequency components, out of these frequency components, let us consider that the highest frequency component is fm, this one, fm, the highest frequency component. So if fm is the highest frequency component, then fs, that is the sampling rate, must be greater than or equal to twice of the maximum sampling frequency, means greater than equal to twice the maximum frequency component. That is called the sampling theorem. And obviously you can understand that undersampling results in signal distortion. So if the sampling rate is not followed, if the rate of sampling is not followed according to the sampling theorem, then there might be problems and that may result in signal distortion. Okay. So this is the effects, as you can see in the first diagram. This is oversampling. It's okay, absolutely fine. You can reconstruct the signal. This is perfect sampling, that is fs equal to 2 fm. But this you can see, the last diagram, fs less than 2 fm, this is undersampling. So if undersampling is there, you see that the signals overlap between each other. So as a result of this overlap, what happens is that the signal gets distorted and we are unable to recover back the original signal from the discrete time signal. So what is the importance of the sampling theorem? Most important, it helps us to identify the exact sampling rate. It gives the way for proper reconstruction of a sampled signal. So without the sampling theorem, it gives a benchmark as to how much rate, as to at what rate we must sample the signal in order to get it back. To summarize, sampling is nothing but it's a conversion of a continuous time signal to discrete time signal. Reconstruction, yes, it's the reverse of sampling, it's the opposite of sampling. So first order reconstruction, yes, it's more accurate than zero order reconstruction, because first order reconstruction uses a triangular pulse, zero order reconstruction uses only a rectangular pulse. Okay. So now sampling theorem says that fs must be greater than equal to 2 fm. We have learned that this is also called Nyquist's sampling rate. And yes, sampling theorem gives a benchmark for the ideal rate of sampling. So thank you for listening to my lecture with patience. If you have any queries, you can kindly mail me in the given mail address. Thank you so much.